Imagine I handed you a teaspoon. An ordinary teaspoon, the kind you stir your coffee with. And imagine that on that teaspoon was a small amount of a certain substance. A substance that exists out in the universe, but cannot be found anywhere on Earth. Not in any laboratory. Not under any pressure we can create. Not in any form we can hold. And imagine that the moment I placed that teaspoon in your hand, the floor beneath you shattered, and the ground gave way, and the teaspoon and everything around it plunged straight down through the earth, because the small amount of substance on that spoon weighed as much as a mountain. As much as a mountain. A single teaspoonful, weighing hundreds of millions of tons, more than a great peak of rock, more than anything you could ever lift or move or imagine. All of it concentrated into a sample small enough to balance on a piece of cutlery. This substance is real. It exists right now, out in the depths of space, in objects scattered across our galaxy, the crushed and impossible remnants of dead stars. They are called neutron stars, and they are among the strangest and most extreme objects in the entire universe. Things so dense, so violent, so far beyond anything in human experience, that they sit right at the very edge of what the laws of physics will even allow to exist. A neutron star is what you get when you take more mass than our entire sun and crush it down into a ball the size of a city, until matter itself is squeezed past every limit we thought it had, into a state so dense that the normal rules simply break down. And the most unsettling thing about them is not even their density, staggering as it is. It is that a neutron star is matter pushed to the absolute brink, balanced on a knife's edge, one small step away from collapsing entirely into something even more terrifying. The densest thing that can exist while still being matter at all, a frozen instant of catastrophe, hanging in the dark. And the truly remarkable thing is that these are not rare freaks, not one-of-a-kind curiosities, tucked away in some distant corner of the universe. Our galaxy alone is thought to contain hundreds of millions of them, the accumulated remnants of all the massive stars that have lived and died over billions of years, scattered throughout the galaxy, most of them dark and silent and undetectable. A vast hidden population of crushed stars, threaded invisibly through the spaces between the living ones. Every massive star that has ever died and left behind such a remnant has added one to the count, and they endure for ages, so they accumulate, an enormous graveyard of dead giants, filling our galaxy, mostly unseen. The night sky, you know, with its scattering of visible stars, is overlaid by a far larger and invisible population of these dead, dense remnants, present in staggering numbers, woven through the galaxy all around us. We have detected only a tiny fraction of them, the ones that happen to sweep a beam toward us, or otherwise reveal themselves. But they are out there in their hundreds of millions, a quiet, crushed multitude. Tonight we are going to journey into one of the most extreme objects the universe can produce, and we are going to understand exactly why it should not, by any intuition we possess, be able to exist. We are going to learn how a star is crushed into such a thing, the violent process that compresses the core of a giant into a city-sized sphere of impossible density. We are going to stand in our imagination on its surface, where gravity is so ferocious that a fall from a height of a single inch would release the energy of a bomb, where the tallest mountains are a few millimeters high, and where you yourself would be flattened into a smear of atoms in an instant. We are going to descend through its bizarre layers, past a crust harder than anything else in the universe, into a strange interior where matter twists into forms that have no name in ordinary experience, down toward a core whose true nature remains one of the great unsolved mysteries of physics. And we are going to confront the knife's edge on which the whole impossible object balances, the razor-thin line between a neutron star and total collapse black hole, the boundary at the very end of what matter can be. But before we can understand the object, we have to understand how the universe makes such a thing, because nothing in everyday experience could ever produce matter this dense. You cannot squeeze it into being. No machine, no explosion, no pressure we can generate comes within an unimaginable distance of what it takes. It requires the death of a star, and a very particular and violent kind of death, the collapse of a giant under its own colossal weight. Out in the galaxy, there are stars far larger than our sun, blazing giants that burn through their fuel at a furious rate and live fast and die young. Throughout their lives, these stars are locked in a battle, a standoff between two enormous forces. On one side, gravity, the relentless inward pull of all the star's mass, forever trying to crush it down toward its center. On the other side, the outward pressure of the nuclear furnace burning in the star's core, the fusion of light elements into heavier ones, pouring out energy that pushes back against gravity and holds the star up. For millions of years, the two forces balance, and the star shines, stable, in a tense equilibrium. But the fuel is finite, and when a massive star finally burns its way to a core of iron, the furnace can give no more, because iron cannot be fused to release energy. The fire at the heart of the star goes out, and gravity, which has been waiting, patient and relentless, for the star's entire life, finally wins. What happens next is almost too fast and too violent to comprehend. The core of the star, no longer held up, collapses, and it collapses with breathtaking speed and force, a core larger than the Earth falling inward and crushing down in a fraction of a second. The matter is squeezed so hard, so suddenly, that something extraordinary happens to it. Something that transforms ordinary matter into the impossible substance we are talking about. To understand it, you have to understand what ordinary matter actually is, and just how much empty space is hiding inside everything you have ever known. Everything around you, everything you have ever touched, is made of atoms, and an atom is almost entirely empty space. At the center of each atom sits a tiny, dense nucleus, and around it, at a great distance, a cloud of electrons. But the scale of that emptiness is hard to grasp. If you blew up an atom until its nucleus was the size of a marble, the nearest electron would be hundreds of meters away, and everything in between would be nothing, pure void. The atom, and therefore all matter, is more than 99.999% empty space. The solid table, the solid ground, your own solid feeling body are almost entirely nothing, vast vacant gulfs with tiny specks of matter scattered through them, held apart by forces, giving the illusion of solidity. The actual stuff, the nuclei where nearly all the mass resides, takes up almost none of the volume. If you could somehow Remove all that empty space from a person. Squeeze out the void and pack the nuclei together, touching. The entire human being would shrink to something smaller than a speck of dust, while keeping all of their mass. This fact alone deserves a moment, because it is genuinely staggering, and almost no one ever stops to feel it. The solidity you experience, the firmness of your own hand, the resistance of the floor, the substance of every object you have ever touched is almost entirely an illusion created by forces, not by stuff. The actual matter, the nuclei, where virtually all the mass lives, occupies a vanishingly tiny fraction of the volume. The rest is empty space, held open by the electric repulsion between the electron clouds of atoms. When your hand presses on a table, the atoms never actually touch. Their electron clouds repel each other across the void, and that repulsion is what you feel as solidity. You have never, in your entire life, truly touched anything. You have only ever felt the push of these forces across the empty gaps between atoms. The whole solid-seeming world is mostly nothing. A sparse scattering of tiny dense specks suspended in vast emptiness, propped up by invisible forces, giving the convincing impression of substance where there is almost none. And a neutron star is what happens when that illusion is stripped away, when the forces are overwhelmed and the void is crushed out, leaving only the dense specks, packed together with nothing in between. This is the key to the neutron star, and it is what makes its density possible. In the collapsing core of the dying star, gravity becomes so overwhelming that it does exactly this. It crushes the atoms out of existence. The electrons, normally orbiting at a great distance, are driven inward, slammed into the nuclei, with such force that they merge with the protons there. And in that merger, electron and proton combine to become a neutron. Across the entire collapsing core, this happens to virtually all the matter at once. The atoms are destroyed, their empty space eliminated, their electrons forced into their nuclei, and what is left is almost pure neutrons, packed together directly, touching, with no empty space between them at all. The matter is no longer a collection of mostly empty atoms. It has become a single, vast, continuous mass of neutrons, packed to the density of an atomic nucleus, but on the scale of an entire star's core. This is neutron matter, and it is the densest, stable substance the universe can make, and as the core collapses, and this transformation happens, something stops the fall, because neutrons, like all particles of their kind, obey a strange and fundamental rule of nature, a rule that forbids them from being squeezed too close together, from occupying the same state in the same place. As gravity crushes the neutrons tighter and tighter, this rule pushes back, harder and harder, generating an outward pressure that has nothing to do with heat or fusion, a pressure that arises purely from the deep quantum nature of the particles themselves, from their fundamental refusal to be packed beyond a certain point. And at a certain density, this pressure becomes strong enough to halt the collapse. The infalling core, plunging inward, slams into this wall of resistance and stops. Suddenly, violently, the collapse arrested in an instant by a force written into the very fabric of matter. The core has become a neutron star, and the abrupt halt of its collapse sends a shock wave, blasting back outward through the rest of the star, helping to drive the titanic explosion of the supernova that announces across the universe that a giant has died and left behind one of these impossible objects. It is worth understanding that a neutron star is only one of three possible fates for a star, because the fork in the road illuminates just how special and finely balanced a neutron star is. The deciding factor is mass. A star like our Sun, when it dies, is not massive enough to crush its core into neutron matter at all. It ends instead as a white dwarf, a dense ember, to be sure, but one held up by the resistance of its electrons before they are ever forced into the nuclei, a far gentler form of compression, dense but nothing remotely like nuclear density. Only stars considerably more massive than the Sun have cores heavy enough that, when they collapse, gravity overwhelms even the electrons and forces the creation of neutron matter, leaving behind a neutron star. So a neutron star requires a star in a particular range of mass, big enough to crush its core past the white dwarf stage into neutron matter, but, crucially, not so big that it goes further still. Because there is a third fate beyond the neutron star, for the very most massive stars of all. If the collapsing core is too heavy, then, as we will see, even the fierce quantum resistance of the neutrons is not enough to halt the collapse, and the core does not stop at a neutron star at all, but continues all the way down into a black hole. So the three fates line up along a scale of mass. The lighter stars become white dwarfs, the heavier ones become neutron stars, and the heaviest of all become black holes. The neutron star occupies the narrow middle ground, the result of a collapse violent enough to make neutron matter, but not so violent that it sails past into total collapse. It is a kind of cosmic threading of the needle, a stellar death that lands in exactly the range where matter is crushed to its absolute limit, and then just barely holds. That a neutron star exists at all is a matter of falling into precisely the right window of mass, neither too little nor too much, a narrow band between the gentle ember and the bottomless abyss. So that is what a neutron star is, at its most basic. The crushed core of a dead giant, more massive than the Sun, compressed into a sphere only a dozen or so kilometers across, made of matter packed to nuclear density, held up against total collapse only by the deep-laid quantum resistance of its neutrons. But to state it that plainly is to drain it of the genuine horror and wonder of the numbers involved, because the numbers are where the real strangeness lives. So let us slow down and actually try to feel the scale of what we are describing, because a neutron star is not just dense. It is dense in a way that breaks the human mind's ability to imagine it. Start with the basic comparison and let it sink in slowly. Our Sun is enormous. It is so large that more than 1 million Earths could fit inside it. It contains the overwhelming majority of all the matter in our entire solar system. Every planet, every moon, every asteroid combined being a mere rounding error next to the mass of the Sun. It is, by any human standard, an object of unimaginable size and mass. Now take more than the entire mass of the Sun, and compress it down, not to the size of a planet, not to the size of a country, but to the size of a city. A sphere, perhaps 20 kilometers across, small enough that you could drive across it in a few minutes, small enough to sit comfortably within the boundaries of a large town. More than the mass of the Sun, in a ball you could walk across in an afternoon, if it were not, of course, instantly lethal in every conceivable way. That is the compression we are talking about. The Sun shrunk to a city with all its mass intact. To make the leap in scale vivid, hold both ends of it in your mind at once. On one end, the Sun, an object so vast that its diameter is more than 100 times the Earth's, a sphere so enormous that light, the fastest thing there is, takes seconds just to cross it. On the other end, a sphere small enough to fit comfortably inside the limits of a city, a ball you could, in principle, circle on foot in an afternoon. And you must take all the matter of the first and pack it, every bit, into the second. It is as if you took the entire ocean and compressed it into a single drop, or took a mountain range and squeezed it into a grain of sand, except far more extreme than either. The factor by which the Sun's matter must be compressed to make a neutron star is so large that ordinary comparisons fail. It is a shrinking of volume by a factor of trillions upon trillions. The largest object you can easily imagine crushed down to one of the smallest, with nothing lost but the empty space. All the mass retained, packed into the tiny remainder. This is the central, staggering fact of a neutron star. And everything else about it, the gravity, the spin, the strange matter, all flows from this one extreme, a star's worth of mass in the volume of a town. This means the density is something the human mind has simply never had to deal with. We measure density by how much mass is packed into a given volume, and the densest ordinary materials we know, the heaviest metals, things like osmium or gold, are dense enough that a small block of them is surprisingly heavy in the hand. A neutron star is denser than those metals, not by a little, not by double or triple, but by a factor of roughly 1,000 trillion. 1,000 trillion times denser than the densest metal on Earth. This is the density of the atomic nucleus itself, the tiny core at the heart of every atom, except spread across an entire object the size of a city. You are no longer dealing with a material in any ordinary sense. You are dealing with bulk nuclear matter, a star-sized atomic nucleus, a thing with no parallel in any human experience. And this is where the teaspoon comes in, the image we started with, because it is the way physicists most often try to convey the unconveyable. Take a single teaspoon and fill it with neutron star material. That teaspoon now holds a sample of matter weighing somewhere in the range of hundreds of millions to 1 billion tons. Let that number actually land. Not hundreds of tons, not thousands, hundreds of millions of tons in a teaspoon. That is the weight of a small mountain, the weight of every car on Earth, combined many times over. The weight of a vast fleet of the largest ships ever built, all concentrated into a volume you could fit in your mouth. If such a teaspoon of material could somehow exist on Earth, which it cannot, it would not sit on your table. It would punch through the table, through the floor, through the foundations of the building, through the soil and the bedrock beneath, falling and falling, crushing everything in its path, plunging down through the body of the Earth itself, because nothing we have, no material, no structure, could possibly support that much weight in that small a space. People have tried many ways to make this density imaginable, and they all sound like exaggerations, even though they are literally true. All of humanity, every single one of the billions of people alive, if you removed the empty space from all of their atoms and packed the remaining nuclear matter together, would fit into a volume about the size of a sugar cube, and that sugar cube would have the density of a neutron star. the entire human race in a sugar cube. Or consider it the other way, a piece of neutron star material the size of a single grain of sand would weigh as much as a large building. A chunk the size of a sugar cube would outweigh a mountain. There is no way to handle these numbers that makes them feel reasonable, because they are not reasonable. They describe a state of matter so far outside our experience that our intuitions have nothing to grab onto. And consider what this density means about the nature of the object as a whole, because it is stranger than just a very heavy ball. A neutron star is not like a planet with a surface you stand on and a distinct interior far below made of different materials, layers of rock and metal arranged by chemistry. It is, in effect, a single colossal nucleus, the mass of a star bound together not loosely, the way a planet's rock is held by ordinary chemistry, but with matter packed to the density of nuclear material throughout. There is no soft ground, no loose soil, no real atmosphere, just that flat, hard, crushed shell, and beneath it, the densest matter the universe permits, all the way down. To call it a star is almost misleading, because it is nothing like the warm, diffuse balls of glowing gas we usually mean by that word. It is something else entirely, a new kind of object, a star-sized piece of nuclear matter, a thing for which our ordinary categories barely have a place. It is matter itself pushed to a form so extreme that the very words we use, surface, ground, substance, strain and nearly break in the describing. And yet, out in the galaxy, there are objects made entirely of this stuff. The mass of suns compressed into the size of cities, hundreds of millions of tons, crammed into every spoonful, real, physical things, spinning in the dark. It helps to understand why we can never make such matter on Earth, because the impossibility is total. Not merely a matter of needing a bigger machine. To compress matter to nuclear density, you have to overcome the fierce resistance of the atoms themselves, the electric forces that hold their electron clouds apart and give matter its solidity. Those forces are not gentle. They are what make a table feel solid, what keep your hand from passing through a wall. To crush them, to force the electrons down into the nuclei, requires a pressure so immense that nothing we can generate comes within a vast distance of it. Our most powerful machines, our most extreme laboratory pressures, are like a feather's touch compared to what is needed. The only thing in the universe that can supply such pressure is the crushing weight of a star's own collapsing mass. Gravity gathered on the scale of an entire stellar core, pressing inward with a force that no engineered device could ever reproduce. Neutron matter cannot be manufactured. It can only be born in catastrophe, in the gravitational collapse of something enormous, which is why it exists only out there, in the corpses of dead giants, and never here. And there is a further consequence of this that is worth sitting with. If you could somehow obtain a piece of neutron star matter and bring it to Earth, it would not remain neutron star matter. The only thing holding it in that crushed state is the colossal gravity of the whole star pressing in on it. Remove it from that gravity, take away the pressure, and the matter would explode violently and instantly, expanding back toward ordinary density with a release of energy beyond any bomb as the crushed neutrons sprang apart, freed from the gravity that had been forcing them together. Neutron matter is not stable on its own. It is held in its impossible state only by the relentless gravitational squeeze of the entire object. It is a substance that can exist only deep inside a neutron star, under the weight of the whole, and nowhere else. You could never hold it, never study a sample, never keep it in a jar. The moment it left the star, it would cease to be what it was, erupting back into ordinary matter in a flash of unimaginable violence. The teaspoon that weighs a mountain can only weigh a mountain, while it remains buried in the crushing heart of a dead star. Now, where there is that much mass packed into that little space, there is gravity, and the gravity of a neutron star is as far beyond our experience as its density. Gravity depends on how much mass there is and how close you can get to it. And on a neutron star, you have more than the mass of the sun, and you can get astonishingly close to its center, because the whole thing is a dozen kilometers across. The result is a gravitational field of monstrous, unimaginable strength. The pull of gravity at the surface of a neutron star is somewhere around 100 billion times stronger than the gravity you feel standing on the Earth. 100 billion times. There is no gentle way to describe what that would do to anything that approached it. Consider what it would mean for you if you could somehow be transported to hover just above the surface of one of these objects, ignoring for the moment the dozens of other things that would kill you instantly. Under Earth's gravity, you have a weight, a comfortable, familiar weight that your legs carry without effort. Near the surface of a neutron star, that same body would weigh, in effect, more than every human who has ever lived combined, crushed downward by that 100 billion-fold gravity. You would not stand. You would not fall, exactly, in any way you could perceive. You would be instantly and utterly flattened, pulled apart and smeared across the surface, your every atom crushed down into the thin layer of matter that coats the star, your existence as a structured object ending in a fraction of an instant. There would be no sensation, no time to feel anything. Just immediate, total annihilation by gravity alone. The gravity is so extreme that it does strange things even to light, the fastest thing in the universe. Near a neutron star, the gravitational field is strong enough to noticeably bend the path of light passing by, curving the rays as they travel, warping the appearance of everything in the star's vicinity. The effect is so pronounced that, if you could somehow observe a neutron star from nearby and survive, you would see something impossible. The gravity would bend the light, coming from the far side of the star around toward you, so that you could see not just the hemisphere facing you, as you would with any normal object, but partway around the back as well, the surface appearing to wrap toward you, more than half the star visible at once, its far side curving into view through the bent light. The star would look swollen, distorted, its surface features smeared and shifted by the warping of the light leaving it. This is the same warping of space and time that, pushed just a little further, creates a black hole. And a neutron star sits close enough to that extreme that the warping is already dramatic, already bending light into impossible paths, already distorting the view of the cosmos in its immediate neighborhood. The object does not just sit in space. It visibly deforms the space and the light around it, a knot of warped reality, a preview of the total warping that lies just beyond it. And the strangeness goes further, into the shape of the object itself. On Earth, Mountains can rise kilometers into the sky because Earth's gravity is weak enough to permit it. On a neutron star, gravity is so overwhelming that it flattens everything, crushing the surface into an almost perfect sphere, smoother than anything in human experience. The tallest possible mountain on a neutron star, the highest that its incredible gravity would permit to exist before crushing it flat, is measured not in kilometers, not in meters, but in millimeters. A bump a few millimeters high would be a towering peak on a neutron star, the Everest of that world, an almost imperceptible ripple on a surface ground flatter than a polished ball bearing. And to climb even that millimeter-high mountain, to lift yourself that tiny distance against that gravity, would require more energy than you could imagine. In fact, the energy released by an object falling on a neutron star is staggering. Drop something from a height of just 1 meter onto the surface of a neutron star, and by the time it hits, it would be traveling at a significant fraction of the speed of light, and the energy released on impact would rival a nuclear explosion. A pebble falling a single meter, hitting like a bomb. That is the gravity we are talking about. It is almost impossible to keep these facts in proportion, because each one alone would be the most extreme thing you had ever heard. And a neutron star has all of them at once. A pull 100 billion times Earth's, mountains measured in millimeters, an escape speed of half the speed of light, a pebble striking like a bomb. Any single one of these would mark an object as utterly beyond ordinary experience. And the neutron star possesses every one of them together, simultaneously, in the same small sphere. There is no aspect of its gravity that is anything less than staggering, no way to soften or downplay any part of it. It is extremity heaped upon extremity, a catalogue of impossibilities all true of the same object, and the only honest response to the list is a kind of stunned disbelief that such a thing can exist at all, and yet it does, in great numbers, scattered through the dark. There is one more number that captures the violence of this gravity, and it is perhaps the most striking of all. To escape from the surface of a world, you have to reach what is called escape velocity, the speed you need to break free of its gravity. On Earth, that speed is about 11 kilometers per second, fast but achievable by our rockets. To escape from the surface of a neutron star, you would need to be moving at roughly half the speed of light. Half the speed of light just to climb away from its surface. Nothing we could ever build could come remotely close. Anything that falls toward a neutron star is accelerated to a substantial fraction of light speed before it arrives, slamming into the surface with cosmic violence. The object sits in space, wrapped in a gravitational field so intense that it noticeably bends the light passing near it, warping the very fabric of space and time around itself. A small, dark sphere whose grip on reality is so fierce that it distorts the cosmos in its immediate vicinity, a city-sized knot of gravity. So tight it is, as we will see, only one step removed from the ultimate gravitational catastrophe. The gravity does something else, too. Something that would destroy you long before you ever reached the surface. And it is worth understanding because it reveals just how violent this gravitational field is. When gravity is this strong, it does not pull on an object uniformly. It pulls much harder on the near side of an object than on the far side, because the near side is closer and gravity weakens with distance. For ordinary gravity, this difference is negligible. But near a neutron star, the gravity is so intense and changes so steeply with distance that the difference in pull between your head and your feet, if you were falling toward it feet first, would be enormous, growing more extreme the closer you came. Your feet would be pulled so much harder than your head that you would be stretched, drawn out, pulled apart lengthwise by the difference in gravitational force across your own body. Long before you reach the surface, you would be stretched into a thin stream of matter, your body drawn into a long thread, then torn apart entirely, your atoms strung out in a line falling toward the star. Physicists have a vivid and slightly grim word for this stretching, comparing it to pulling food into a long, thin strand, and it is one of the ways the extreme gravity of these objects expresses its violence, reaching out to tear apart anything that approaches, not by crushing it all at once, but by stretching it into a thread before it ever arrives. So picture, if you dare, the experience of approaching one of these objects purely as a thought experiment, since no one and nothing could ever survive it. From a great distance, it looks almost unremarkable, a tiny, faint point, far smaller than a planet, easy to overlook. But as you fell toward it, gathering speed, accelerating to a substantial fraction of the speed of light, the gravity would mount utterable swiftness, and the stretching would begin gently at first, and then with mounting violence, until you were drawn out into a thread of matter, torn apart, your remnants slamming into the surface at half the speed of light, vaporized in a flash of energy, spread across that incomprehensibly hard crust. The whole approach, from the first faint sight of the object to total annihilation, would be a swift, brutal, escalating catastrophe, the gravity reaching out across space to stretch and shred and finally obliterate, a demonstration of just how far beyond the gentle pull of our world the gravity of a neutron star truly lies. So far, we have treated the neutron star as a simple ball of neutrons, but the reality is far stranger and more structured than that, because under such extreme conditions, matter organizes itself into layers, each one more bizarre than the last, and descending through them is like descending through levels of increasing impossibility. Let us take that journey inward, from the surface down toward the core, and watch the matter transform as the pressure climbs. At the very surface, there is an atmosphere, though calling it that stretches the word almost to breaking. It is not air. It is a searingly hot, impossibly thin layer of plasma, perhaps only a few centimeters thick and held flat against the star by that crushing gravity, a wisp of superheated matter clinging to the surface. Below it lies the crust, and here we encounter the first of the neutron star's wonders. The outer crust is a crystalline lattice of atomic nuclei packed into a rigid structure. But a structure under such pressure and made of such dense material that it is harder than anything else known to exist. The crust of a neutron star is thought to be billions of times stronger than steel, the strongest solid material in the entire universe. A shell of crushed nuclei so rigid and so resistant that nothing in our experience compares. Try to grasp what billions of times stronger than steel actually means, because it is hard to take in. Steel is to us the very emblem of strength, the material we build our bridges and skyscrapers and ships from. a substance that can bear enormous loads without yielding. And the crust of a neutron star is not twice as strong as steel, or 10 times, or 1,000 times, but billions of times stronger, so far beyond steel that the comparison nearly loses meaning. It is a material that could withstand forces that would shatter or vaporize anything we could build, a solid so rigid that it resists the crushing gravity of the star itself, holding its shape against a pull 100 billion times stronger than Earth's. There is nothing in human engineering, nothing in the natural world we know, that approaches it. It is the strongest stuff there is, forged not in any furnace or factory, but in the crushing aftermath of a stellar collapse, a shell of impossible rigidity, wrapped around the densest matter in the universe. And yet, this incomprehensibly strong crust is only a thin shell, perhaps a kilometer or so thick, wrapped around the vast denser interior. That crust, rigid and immensely strong as it is not perfectly static, and when it shifts, the results are violent. As a neutron star spins, and as its powerful magnetic field tugs and strains against the crust, stresses can build up within that solid shell, just as stresses build up in the rock of the Earth along its fault lines. And just as the Earth's crust can suddenly slip and crack, releasing its stored stress in an earthquake, the crust of a neutron star can suddenly fracture and shift, releasing its stress in what astronomers call a starquake. But a starquake is to an earthquake what a neutron star is to a pebble. The crust that cracks is made of matter billions of times stronger than steel, under stresses beyond imagining. And when it finally gives, the energy released can be staggering, in some cases producing bursts of radiation that we can detect from across the galaxy. A shift in the crust of a neutron star, of even a tiny fraction of a millimeter, can unleash energy that dwarfs anything our planet could ever produce. The surface of these objects, flat and hard and still as it appears, is capable of sudden, catastrophic ruptures, the rigid shell of the dead star cracking under strains that would shatter any ordinary material instantly. These starquakes also reveal themselves in another way, through the spin of the star. Pulsars, as we will see, keep time with extraordinary precision, their rotation so steady that they rival the best clocks. But occasionally, a pulsar is observed to suddenly speed up, its rotation jumping fractionally in an instant, an event astronomers call a glitch. These glitches are thought to be connected to the inner workings of the star, to the interplay between the rigid crust and the strange, superfluid interior beneath it, the sudden transfer of motion between the two, as the crust cracks or the superfluid within shifts its rotation. Each glitch is a window into the hidden interior of the star, a clue to the bizarre physics going on inside, detectable only because these objects keep time so precisely that even a tiny, sudden change in their spin can be measured from light years away. The dead star, silent and remote, betrays the violence of its interior through these sudden hiccups in its otherwise perfect rhythm. As you descend into the crust, the pressure climbs, and the matter begins to do something genuinely strange, something that has earned the matter inside a neutron star one of the most delightful and unsettling names in all of physics. In the deeper layers of the crust, the nuclei are squeezed so tightly that they can no longer hold their normal rounded shapes. Forced together by the immense pressure pressure, competing between the nuclear force pulling them together and the electric force pushing them apart. The nuclear matter is squashed and stretched into bizarre, elongated, flattened forms. Physicists, studying these shapes in their models, noticed that they looked remarkably like types of pasta. And so the matter deep in a neutron star's crust is officially described using those names. There are regions where the nuclei are squeezed into long strands, like spaghetti. Regions where they are flattened into broad sheets, like lasagna. Regions of little blobs, like gnocchi, and tubes, and other shapes. A whole menu of nuclear pasta, layered through the deep crust of the star. It would be almost whimsical if it were not a description of matter under pressures that would obliterate anything we know, exotic states of nuclear material existing nowhere in the universe except the crushing interiors of these dead stars. Try to picture the descent, layer by layer, as a kind of impossible elevator ride downward into the star. Even though no such journey could ever be made, you begin at the surface, on that flat, hard, almost perfectly smooth shell, with its searing thin atmosphere clinging above. You pass into the outer crust, a crystalline lattice of crushed nuclei, the strongest solid in the universe, growing denser with every meter. As you go deeper, the pressure climbs relentlessly, and the matter begins to change. The neat nuclei first deforming, then merging, then flowing into those bizarre pasta shapes, the gnocchi and spaghetti and lasagna of nuclear matter, each layer denser and stranger than the one above. Every step downward takes you into conditions more extreme than any that exist anywhere on Earth or in any laboratory, into states of matter that have no name in ordinary experience, that exist only here in the deep interior of a dead star. And you are still only in the crust. Below the pasta lies the vast interior, denser still, where the matter changes yet again, and below that the mysterious core. The descent is a journey through escalating impossibility, each layer a new regime of physics, the matter transforming again and again as the crushing pressure mounts, all of it sealed away forever beneath a surface that would annihilate any traveler in an instant. And this nuclear pasta is not just strange to look at in a model. It is thought to be, by a wide margin, the strongest material in the entire universe, far stronger even than the already incomprehensibly strong crust above it, perhaps 10 billion times stronger than steel. The most rigid and resistant substance that physics permits to exist. To break it would require forces beyond anything in the cosmos, short of the gravity of the star itself. It is a material made of nuclear matter squeezed into impossible shapes, lining the deep interior of an object that should not exist. And it represents the absolute pinnacle of material strength in all of nature, a substance so far beyond steel or diamond or anything we can manufacture that the comparison becomes almost meaningless. Nothing we will ever build, no alloy, no engineered material, no laboratory creation, will come within an unimaginable distance of it. It is simply the strongest matter the universe is capable of forming anywhere, by any process, and it exists only here, buried in the deep crust of a dead star, far from any hope of being seen or touched. Below even this, as we descend further, the matter changes again, dissolving past the pasta into something even stranger, a vast ocean of free neutrons. And here the matter takes on a property that seems to belong to a different world entirely. Beneath the crust, in the outer core of the neutron star, the matter becomes a fluid, an ocean of densely packed neutrons. And this ocean has a property so strange, it seems to defy common sense. It is thought to be a superfluid. A superfluid is a state of matter that flows with absolutely zero friction, zero resistance, zero viscosity. On Earth, scientists can create superfluids only in tiny quantities, by cooling certain substances to within a hair of the coldest temperature, physically possible, near absolute zero, and even then the effects are subtle and fragile. A superfluid, once set swirling, would circulate forever, never slowing, never stopping, because there is nothing to slow it down, no friction to drain its motion. It can climb the walls of its container, flow through impossibly tiny gaps, behave in ways that look almost alive. And the interior of a neutron star is thought to be a vast, churning ocean of this frictionless neutron superfluid, swirling endlessly within the crushing dark of the star, an enormous sea of the most exotic fluid in nature, larger than any superfluid that could ever exist on Earth by an unimaginable factor. To grasp how bizarre a superfluid is, consider what physicists observe in the tiny samples they can make in their coldest laboratories. A superfluid, having no friction whatsoever, behaves in ways that seem to violate common sense. Set it spinning, and it will not form a smooth, rotating whirl the way ordinary water does. Instead, it organizes itself into a precise array of tiny, individual whirlpools called vortices, each one a perfect, frictionless tornado, the rotation of the whole fluid carried entirely by these quantized whirlpools. A superfluid can creep up and over the walls of its container, climbing against gravity in a thin film, escaping any vessel that tries to hold it. Poured, it can flow through gaps so small that no ordinary liquid could pass. It is matter behaving according to the strange rules of the quantum world, but on a scale large enough to see, a substance that seems almost to have a will of its own. And the interior of a neutron star is filled with this stuff. On a colossal scale, a vast, frictionless ocean, threaded with countless quantized vortices, swirling endlessly in the crushing dark, an entire sea of the most counterintuitive fluid in nature, sustained not by extreme cold, as on Earth, but by the extreme density at the heart of a dead star. And alongside the superfluid neutrons, the smaller number of protons in the core are thought to form a superconductor, a state in which electricity flows with zero resistance perfectly forever. So the core of a neutron star may be, simultaneously, the largest superfluid and the largest superconductor in the universe, a place where the most delicate and exotic quantum states we can barely coax into existence in our most advanced laboratories, exist naturally on a colossal scale, sustained by the very conditions that would destroy any ordinary matter. The interior of a dead star is, in this sense, a quantum laboratory beyond any we could ever build, hosting states of matter at scales and conditions we cannot remotely approach, deep inside an object whose surface would annihilate us in an instant. But the true heart of the neutron star, the very center, the inner core, is one of the genuine unsolved mysteries of modern physics, and this is where the story becomes most tantalizing. As you go deeper, the density climbs even higher, past the density of an ordinary atomic nucleus, into a regime that we cannot reproduce anywhere on Earth and cannot fully describe with our current theories. What happens to matter when it is squeezed even beyond nuclear density? We do not know for certain. Our equations become uncertain. Our experiments cannot reach those conditions. The center of a neutron star is a place where the laws of physics, as we understand them, run out, where matter is pushed into a regime we have never observed and cannot recreate, and where, as a result, we are genuinely unsure what exists. There are possibilities, and they are exotic. Perhaps the neutrons themselves break down. Neutrons, it turns out, are not the most fundamental things. They are made of smaller particles called quarks, normally bound up tightly inside, never seen alone, but at the unimaginable pressures of a neutron star's core. Perhaps the neutrons are crushed so hard that they dissolve, their quarks, set free to swim in a dense soup, a state of matter that has never been seen, and that would be its own kind of impossible substance, a quark fluid at the heart of the star. Dwell for a moment on how radical that possibility is. Quarks are, as far as we know, among the most fundamental building blocks of matter. The tiny particles that combine to make the protons and neutrons that make up everything. And one of the deepest features of how nature works is that quarks are never found alone. They are bound together so tightly inside particles like neutrons that no force we can apply has ever pried a single one loose. Try to pull quarks apart, and the force binding them only grows stronger, so they remain forever confined, locked inside their particles. It is one of the firmest rules of the subatomic world. And yet, at the heart of a neutron star, under pressures beyond anything we can create, that rule may be broken. The neutrons may be squeezed so hard that they lose their individual identities, dissolving into a shared sea of quarks no longer confined to separate particles, free to mingle and flow, a state of matter in which the most fundamental building blocks, normally locked away forever, are set loose and packed together directly. If that is what lies at the center of a neutron star, then these objects contain a form of matter more fundamental and more exotic than anything we have ever observed. A glimpse of what the building blocks of reality do when crushed beyond the point where ordinary particles can survive. Or perhaps the matter takes on other strange forms we have only theorized, involving heavier and more exotic particles, or states with properties we can barely guess at. The point is that we do not know. At the center of one of the most extreme objects in the universe lies a question mark, a region whose contents we cannot determine, a genuine frontier of physics hidden inside the crushed corpse of a star, the answer locked away behind a surface no probe could ever survive to reach. And yet, remarkably, scientists are not entirely helpless before this mystery, because the nature of the core leaves subtle fingerprints on properties we can measure from afar. The key is something called the relationship between a neutron star's mass and its size, depending on what the matter in the core is actually made of, on how stiff or soft it is, on how strongly it resists further compression. A neutron star of a given mass will be slightly larger or slightly smaller. A stiffer interior, one that resists compression strongly, produces a somewhat larger star. A softer interior, one more easily squeezed, produces a smaller one. So, if we can measure both the mass and the size of a neutron star precisely enough, we can begin to deduce what its hidden interior must be like, reading the nature of the unknowable core from the dimensions of the star as a whole. This is fiendishly difficult, requiring exquisitely careful observations of these tiny, distant objects, but it is being done with specialized instruments designed to measure the sizes of neutron stars. By watching the radiation from their surfaces, slowly narrowing down the possibilities for what lies within. And there is another spectacular way the core reveals itself: when two neutron stars collide. When a pair of these objects spiral together and merge, the way they distort each other in the final moments before impact. The way each one's gravity stretches and squeezes the other depends sensitively on how stiff or soft their interiors are, on the nature of the matter in their cores. And those final moments send out ripples through the fabric of space itself, ripples we have learned to detect with instruments of astonishing sensitivity. By measuring those ripples, by reading the precise way two neutron stars deformed each other as they died together, scientists can extract clues about the matter inside them, about that unreachable core, from the gravitational echo of their collision. It is an extraordinary thing. We are learning about the most inaccessible matter in the universe, the stuff at the heart of a neutron star that no probe could ever touch, by listening to the ripples in space made when two of these objects are destroyed. The core hides behind a surface that would annihilate anything, and still, through cleverness and patience and remarkable instruments, we are slowly prying loose its secrets, reading the unreadable interior from the size of the star and the echoes of its death. There is another property of neutron stars that is just as extreme as their density and their gravity, and it is the reason we ever discovered them at all. They spin and spin at speeds that, like everything else about them, seem impossible. To understand why, think of a figure skater spinning on the ice. When the skater pulls their arms in close to their body, they spin faster, dramatically faster, because of a law of physics that conserves spin, that demands that as something shrinks, it must rotate more quickly to make up for it. Now apply that to a star. The original giant star was rotating slowly, as all stars do, taking perhaps weeks or months to turn once. But then its core collapsed, shrinking from something larger than the Earth down to a sphere a dozen kilometers across. An enormous contraction, and just like the skater pulling in their arms, but to an extreme almost beyond comprehension, the collapsing core spun faster and faster as it shrank until the resulting neutron star was rotating at a blistering, ferocious rate. How fast? A newly formed neutron star can spin many times every second. Some of them, the fastest, spin hundreds of times every single second. Picture that. An object more massive than the sun, a sphere the size of a city, made of matter packed to nuclear density, rotating not once a day, not once an hour, but hundreds of times per second, its surface whipping around at a substantial fraction of the speed of light. The entire massive object, turning so fast, it completes hundreds of full rotations in the time it takes you to blink. It is one of the most violent and energetic forms of motion in the universe, a colossal mass spinning at a frequency we would normally associate with a sound wave or an engine, a city-sized nuclear object whirling like a dynamo in the dark. It is worth pausing to feel how violent that rotation truly is at the surface. Take a neutron star, spinning hundreds of times a second. a sphere perhaps 20 kilometers across. The material at its equator, whipping around the full circumference hundreds of times every second, is moving at a substantial fraction of the speed of light, tens of thousands of kilometers every second, a speed that dwarfs anything in human experience by an incomprehensible margin. The surface of the star is in effect being flung outward by this ferocious spin, and only the object's monstrous gravity, that 100-billion-fold pull, is strong enough to hold it together against such rotation. A lesser object spinning that fast would tear itself apart instantly. So the neutron star is locked in yet another extreme balance. Its furious spin trying to fling it apart, its crushing gravity holding it together. The two enormous forces in tension, the object stable only because both are pushed to such extremes that they can match each other. It is, in every respect, an object of balanced violence, density balanced against quantum resistance, spin balanced against gravity, every property cranked to an extreme and held in a tension that would destroy anything less. The serene, regular tick of the pulsar that we detect from light years away is the calm outward face of an object that is, internally, a maelstrom of balanced cosmic forces, a dynamo of crushed matter spinning at the edge of what rotation itself can survive. And as these objects spin, many of them sweep beams of radiation out into space, like the rotating beam of a lighthouse. A neutron star can channel powerful beams of radio waves out from its magnetic poles, and as the star rotates, those beams sweep around through space. If one of those beams happens to point toward Earth, then, once every rotation, as the beam sweeps across us, we detect a pulse, a brief flash of radio energy, and then nothing until the next rotation brings the beam around again. The result is a stunningly regular series of pulses, tick, 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 with the precision of a clock, sometimes hundreds of times a second, arriving from a point in the sky. These pulsing neutron stars are called pulsars, and they are among the most precise natural clocks in the universe. Their pulses so regular that they rival atomic clocks in their steadiness. And it was these pulses that first revealed neutron stars to humanity, in a discovery that is one of the great stories of modern astronomy. In the late 1960s, a young researcher named Jocelyn Bell, studying signals from the sky with a radio telescope, noticed something strange in her data. A regular, repeating pulse, arriving with such clockwork precision that it seemed almost artificial. The regularity was so perfect, so unlike anything natural that had been seen before, that for a brief period the researchers half-seriously labeled the signal with a joking name that hinted at the possibility that it might be a beacon from an alien intelligence. So unnatural did its precision seem. But it was not aliens. It was something almost as strange. The first detected pulsar, a spinning neutron star, sweeping its beam across the Earth. The first evidence that these theoretical objects, predicted decades earlier, but never observed, were actually real, actually out there, spinning in the dark. There is something wonderful in that sequence, the prediction long before the discovery. Decades before the first pulse was detected, physicists working through the consequences of their theories had concluded that such objects should exist. They had reasoned that if a star's core were massive enough, the collapse would crush electrons into protons, make neutrons, and produce a tiny, impossibly dense star held up by neutron resistance. It was a bold prediction, made on paper, from pure reasoning about the behavior of matter under extreme gravity. At a time when there was no way to observe such a thing and little expectation that one ever could be. For years it remained a theoretical curiosity, an exotic possibility that might or might not correspond to anything real. And then, decades later, came the pulses, the steady ticking from the sky, and the realization that here was the predicted object, confirmed real, spinning out there exactly as the theory had said it must. It is one of the great vindications in the history of physics, a prediction made from first principles, set aside for a generation, and then dramatically confirmed by an accidental discovery. The theoretical and the observed finally meeting in the steady beat of a pulsar. From that first detection, we now know of thousands of them scattered across our galaxy, each one a dead star, spinning and pulsing, a lighthouse made from the crushed corpse of a giant. The precision of these natural clocks is almost beyond belief, and it has made them one of the most useful tools in all of astronomy. The fastest and most stable pulsars keep time so reliably, their pulses arriving with such perfect regularity, that they rival the best atomic clocks humans have ever built, ticking away with a steadiness that can be predicted years in advance to within fractions of a second. Think about what that means. A dead star, the crushed remnant of a stellar catastrophe, spinning hundreds of times a second, somehow keeps time more reliably than almost anything we can manufacture. Its rotation so steady that astronomers can use it as a reference clock for measuring the universe. We use these pulsar clocks for extraordinary things, to test our theories of gravity with exquisite precision, to detect the faint passage of ripples in space by watching for tiny disturbances in the pulses, even, in principle, to navigate spacecraft across the solar system by triangulating off the steady beats of multiple pulsars, a cosmic positioning system written in the spin of dead stars. The corpses of giants have become some of the most precise instruments in the universe, and we have learned to read them like clocks. And wrapped around all of this is another extreme property we have only touched on: the magnetic field. As the core of the star collapsed, it did not only spin up, it also concentrated its magnetic field, squeezing the field lines closer and closer together until the magnetic field of a neutron star became staggeringly powerful, trillions of times stronger than the Earth's, among the strongest magnetic fields anywhere in the cosmos. It is this colossal magnetic field, spinning with the star, that channels and beams the radiation we detect as pulses, that drives much of the violent activity at the star's surface, that shapes the environment around the object into a maelstrom of energy. The neutron star is not just dense and fast and heavy, it is also one of the most powerfully magnetized objects in existence. A spinning magnet of cosmic proportions, its field reaching out into space and flinging radiation across the galaxy. Every property of these objects, it seems, is pushed to an extreme that beggars the imagination. Density and gravity and spin and magnetism, all simultaneously cranked up to levels found nowhere else, all in the same small, dark, city-sized sphere. Now we come to the most unsettling truth about neutron stars, the thing that makes them Not just extreme, but genuinely terrifying, in a way that goes beyond their density or their gravity. A neutron star is matter at the very edge of existence, balanced on a knife's edge, and on the other side of that edge lies oblivion. To understand this, remember what holds a neutron star up. It is not fusion. The fire went out long ago. It is that deep quantum resistance of the neutrons, their fundamental refusal to be packed beyond a certain density, generating an outward pressure that fights against the relentless inward crush of the star's own gravity. For a neutron star, that resistance is just barely enough. It holds, but only just. Here is the crucial point. That neutron resistance, mighty as it is, has a limit. It can only support so much weight. If a neutron star has too much mass, if it is pushed past a certain threshold, then even the deep quantum resistance of its neutrons is not enough to hold back gravity. And when that happens, there is nothing left. There is no more powerful form of resistance in all of physics. No deeper pressure that can take over. No further stage of matter that can hold the line. The neutron resistance is the last stand, the final wall that matter can put up against the crush of gravity. And if gravity overwhelms that final wall, the collapse does not stop at a denser kind of star. It does not stop at all. The matter collapses completely, crushing down past every limit, down toward a point until it forms the ultimate gravitational catastrophe, an object from which not even light can escape. A black hole. So a neutron star sits at the very boundary, the last threshold before total collapse. It is the densest, most compressed object that can exist while still being matter, while still being a thing with a surface, a structure, a substance you could, in principle, touch. One step further, one bit more mass, and it ceases to be matter at all, and becomes a black hole, a region where matter as we understand it no longer exists, crushed out of being entirely. The neutron star is matter's last stand. It is the final, most extreme form that a substance can take before gravity wins completely. And the very concept of a surface, of stuff, of matter, dissolves into the abyss, and the margin is terrifyingly thin. The difference between a neutron star, a real physical object you could imagine standing on, and a black hole, a hole in the fabric of reality, is just a relatively small amount of mass, a final straw that breaks the back of the neutron resistance and sends the whole tumbling over the edge into total collapse. This is what I mean when I say a neutron star is a frozen instant of catastrophe. It is a collapse that very nearly went all the way, halted at the last possible moment by the final wall. Matter can offer, frozen there, balanced on the brink, a permanent near disaster. And the universe demonstrates this brink directly because neutron stars can be pushed over it. If a neutron star is in orbit with another star and slowly pulls matter off its companion, its mass can creep upward, closer and closer to the threshold, until one day it crosses the line, the neutron resistance fails, and the star that had held itself together for millions of years collapses in an instant into a black hole. Or two neutron stars, orbiting each other, can spiral together and merge, their combined mass blowing past the limit, collapsing into black hole in a cataclysm so violent, it shakes the very fabric of space with ripples we can detect from across the universe. The neutron star is not a permanent, stable resting place. It is a pause, a held breath, matter clinging to existence at the very edge of the abyss, and sometimes that grip fails, and the edge is crossed, and the last wall falls. There is a strange poetry, almost a kind of heroism, in the image of the neutron star holding the line. For millions of years, the star fought gravity with the fire of fusion, and in the end it lost, its fire going out, its core collapsing. And at the last possible instant, with the core plunging inward and nothing left to burn, one final defense rose up: the deep quantum resistance of the neutrons, the most fundamental refusal of matter to be crushed, and it caught the collapse and held it, just barely, at the very brink. The neutron star is matter making its final stand, the last line of defense against total gravitational collapse, holding a position that nothing stronger could hold, balanced at the edge with no further reserves behind it. Every neutron star in the universe is frozen in that posture, that final defiant stand, matter holding the line against gravity at the absolute limit of its strength, having given up every other defense and clinging to existence by its last and deepest resource. And in those cases where the mass is too great, where even that last stand fails, we see what the neutron star is holding back: the complete victory of gravity, the collapse all the way down, the abyss. The neutron star is the line itself, the final boundary, the place where matter makes its last stand against being crushed out of existence entirely. We have actually witnessed this happen in one of the most remarkable observations in the history of science. Out in a distant galaxy, two neutron stars had been locked in orbit around each other, circling closer and closer over millions of years, each one a crushed sphere of nuclear matter, spiraling inward as they lost energy to the ripples they cast into space. And then, in their final moments, they fell together and merged, their combined mass crashing past the limit that neutron matter can support, the last wall collapsing, the merged object plunging into total collapse. That collision sent out a burst of ripples through the fabric of space itself, gravitational waves that spread across the universe and, after traveling for a vast span of time, washed over the Earth and were detected by instruments so sensitive they can measure a disturbance in space smaller than the width of an atomic nucleus. For the first time, we felt the collision of two neutron stars, the crossing of the boundary, the moment matter gave up its last stand and fell into the abyss, registered as a faint trembling in the fabric of reality, picked up by detectors built specifically to feel such things. And in the same event, telescopes around the world caught the light of the collision, the flash and glow of the merging dead stars' bosses, confirming what the ripples had told us, and revealing something extraordinary about what such collisions produce. Because in the unimaginable violence of two neutron stars merging in the searing conditions of that final catastrophe, heavy elements are forged in great quantity and flung out into space, some of the heaviest and rarest materials the universe contains. The collision of dead stars is one of the cosmic forges where such elements are made, scattered across space, to enrich the gas from which new stars and planets will form. So the crossing of that final boundary, the failure of matter's last stand, is not only an ending but also a kind of seeding, the destruction of the neutron stars, sowing the universe with precious material. The boundary is real, the abyss is real, and we have now both felt and seen. What happens when matter is pushed across it, the ripples, in space and the flash of light together, telling the story of the moment two of the universe's most extreme objects gave way and collapsed. That single event, the detection of two neutron stars merging, was one of the most important moments in the history of astronomy because of what it represented. For the first time, we observed the same cosmic event in two completely different ways at once, feeling it through the ripples it sent through space and seeing it through the light it cast across the cosmos. It was as if, having spent all of history watching the universe in silence, we suddenly gained the ability to both see and hear it at the same time, to perceive a single event through two entirely different senses, and to combine what they told us into a far richer understanding than either could give alone. And the event confirmed in one stroke a whole web of ideas, that neutron stars exist and collide, that such collisions send out ripples in space-time, exactly as predicted, that they forge heavy elements, that they can collapse into black holes. A great many threads of physics came together in that single observed catastrophe, the death of two dead stars in a distant galaxy, felt and seen on Earth long after it happened. A moment when our understanding of these extreme objects was confirmed and deepened all at once. The neutron star, long a creature of theory and faint pulses, had revealed itself in the most dramatic way possible, in the violence of its own destruction, felt in the trembling of space itself. There is something profound and a little humbling about what neutron stars represent for science, and it is worth pausing on. We have here on Earth built extraordinary machines to study matter under extreme conditions, vast particle accelerators that smash particles together at nearly the speed of light, laboratories that can create pressures and temperatures far beyond anything in everyday life. And yet, for all our ingenuity, we cannot come remotely close to the conditions inside a neutron star. We cannot make matter that dense. We cannot reach those pressures. The interior of a neutron star is a regime of physics that is, and may always be, beyond the reach of any experiment we could ever perform on Earth. It is a state of matter we can only study from a distance by observing these objects across the gulfs of space and trying to deduce from the light and the pulses and the ripples they send us what must be going on inside. This makes neutron stars something remarkable, natural laboratories for physics we could never otherwise explore. The universe, in crushing the cores of dead stars, creates conditions that no human technology can match. And in doing so, it runs experiments for us. Experiments in the behavior of matter at the very edge of what is possible. And all we have to do is learn to read the results. When we study a neutron star, we are studying physics at its frontier. Probing the behavior of matter in a regime our equations can barely describe, testing our deepest theories against the most extreme conditions in the cosmos. These objects are how we learn what matter does. When it is pushed past every limit, and the answers they hold are answers we could never get any other way. The dead stars are teachers, holding lessons about the nature of matter that are locked away from us on Earth, written only in the crushed interiors of collapsed giants. This is a genuinely strange position for science to be in, and it is worth dwelling on. Normally, when we want to understand how something behaves, we experiment on it. We take it into a laboratory. We subject it to conditions we control. We measure what happens, and we build our understanding from there. But the matter inside a neutron star can never be brought into any laboratory, never be created, never be controlled or measured directly. It exists only under conditions we cannot reproduce, sealed inside objects we can never visit. So we are forced into a different and more humble mode of science, the mode of the astronomer, who cannot touch the thing being studied, but must instead deduce its nature from the faint signals it sends across space. We learn about neutron star matter not by experimenting on it, but by watching these objects from light years away, measuring their masses and sizes, timing their pulses, feeling the ripples from their collisions, and inferring from all of that indirect evidence what the matter inside must be like. It is detective work on a cosmic scale, reconstructing the nature of the most extreme matter in the universe, from the traces it leaves in the light and the space-time around it. And there is something beautiful in the fact that it works at all, that we can know anything about a substance we can never hold. The matter inside a neutron star is, in the most literal sense, untouchable, forever beyond our direct reach, and yet we have learned a great deal about it, narrowing down its properties, ruling out possibilities, slowly building a picture of the impossible substance at the heart of these dead stars. It is a testament to the power of indirect reasoning, to the ability of the human mind to grasp things it can never touch, to reach across unimaginable distances and crushing impossibilities, and still come away with knowledge. The neutron star keeps its interior locked away, and still, patiently, cleverly, we pick the lock from a distance, learning the secrets of matter at its limit without ever laying a hand on it. And there is a deep strangeness in realizing that the universe routinely produces conditions so far beyond our reach. We sometimes imagine that our laboratories represent the cutting edge of extremity, that with our great machines, we have explored the limits of what matter can do. But the cosmos casually exceeds us, creating in the death of a single star a density and a pressure and a gravity that dwarf anything we can manufacture, not by a little, but by factors so large they have no intuitive meaning. The neutron star is a reminder that the universe is far more extreme than our corner of it, that out there, in the dark, nature performs feats of physics that make our most powerful experiments look gentle, that the quiet, mild conditions of Earth, where matter sits comfortably in its familiar forms, are a tiny and unrepresentative sliver of what is possible. We are, in a sense, spoiled by the gentleness of our home, lulled in to thinking that the calm behavior of matter around us is how matter simply is. But our planet is an oasis of mildness in a universe of extremes. The temperatures, pressures, and gravities we experience are absurdly gentle by cosmic standards, a narrow and comfortable band within which matter behaves in the soft, familiar ways we know. Step outside that band, into the conditions that prevail in the cores of stars and the hearts of dead giants, and matter does things that would seem impossible to anyone who knew only the gentle version. The neutron star is one of the clearest demonstrations of this, a place where matter, freed from the mildness of Earth and subjected to the true extremes the universe can muster, reveals capacities we would never have guessed it had. Our everyday experience of matter is not the rule. It is a gentle exception, a quiet corner, And the neutron star is a glimpse of what the same matter does. Out in the harsher reaches, where the universe shows its true nature. Reality, at its edges, is far stranger and more violent than the calm world we inhabit. And the neutron star is one of the places where that strangeness becomes undeniable. And yet, strange and remote as these objects are, they are connected to you, intimately, through the matter you are made of, in a way that collapses the distance between the impossible neutron star and your own ordinary body. Because the secret of the neutron star's density, remember, is the elimination of empty space, the crushing out of the void that fills all ordinary matter. And that void fills you, too. You feel solid. You feel substantial, dense, real. A body of bone and muscle and flesh that occupies space and resists pressure. But you, like everything else, are almost entirely empty. The atoms that make you up are more than 99.999% void. Tiny nuclei, separated by vast, in relative terms, gulfs of nothing. Your apparent solidity nothing more than the electric forces holding those distant specks apart. If you could remove the empty space from your body, if you could crush your atoms together, the way the dying star's core was crushed, eliminating the void and packing your nuclei directly against one another, your entire body, all of your mass, would collapse to something smaller than a grain of dust, a microscopic speck with the density of a neutron star. Everything that you are, in terms of actual matter, would fit into a volume almost too small to see. The rest of you, the part that gives you size and shape and presence, is empty space. There is something vertiginous in that realization, and the neutron star makes it concrete. A neutron star is simply what matter becomes when that emptiness is taken away, when the void inside the atoms is crushed out, and the nuclei are packed together as tightly as nature allows. It is not made of exotic, alien stuff in the sense of being a different kind of matter from you. It is made of the same nuclear material that sits at the heart of your own. Atoms, the same protons and neutrons, just stripped of the vast empty space that normally surrounds them and packed together directly. In a real sense, a neutron star is what you would be, what anything would be, if the emptiness were removed. It is ordinary matter with its illusion of solidity stripped away, revealing the staggering density that was always lurking inside, hidden by the void. The neutron star is not so much a different substance as a glimpse of what your own substance truly is. Beneath the empty space, when that space is finally crushed out of it, and the connection runs deeper still, into the very atoms of your body, because neutron stars are not just distant curiosities. They have played a role in making the material world around you. When two neutron stars collide and merge in those cataclysmic events at the edge of becoming black holes, the unimaginable conditions forge heavy elements and fling them out into space. Some of the heaviest and most precious materials in the universe, scattered across the cosmos to be woven into new stars and planets. Some of the heavy elements in the world around you, and perhaps in your own body, may trace their origin to the violent collisions of these dead stars. The neutron star, not only a glimpse of what your matter is, but, in part, a forge that helped create some of it. The impossible object in the dark and the ordinary atoms in your hand are not separate things. They are bound together, the extreme and the everyday, the crushed star and the empty body. two faces of the same matter, the same physics, the same universe. This is worth holding on to because it dissolves the comforting illusion that the violence of the cosmos is something entirely separate from us, happening to other alien kinds of stuff, far removed from the gentle matter of our lives. It is not separate, it is the same matter. The protons and neutrons in your fingertips are the same protons and neutrons that, under enough gravity, become a neutron star. The only difference between the calm matter of your body and the crushed matter of a dead star is the conditions, the pressure, the gravity, the circumstances. Change those and your matter would do exactly what the star's matter did. There is no special, gentle kind of matter reserved for us, and a separate, violent kind reserved for neutron stars. There is just matter, the same throughout the universe, behaving gently here in our mild corner and monstrously out there in the crushing dark, the difference lying not in the substance but in what is done to it. You are made of the same stuff that becomes the most extreme objects in the cosmos, and you carry that potential within you, dormant, held back only by the gentleness of your circumstances. So when you contemplate a neutron star, you are not contemplating something wholly alien and removed from yourself. You are contemplating an extreme version of your own substance, a vision of what matter is at its limit, and a reminder that the solid, comfortable, everyday world you inhabit is a gentle and unusual arrangement of a substance that is capable, under the right conditions, of densities and pressures and violence almost beyond imagining. The same stuff that makes your morning coffee and the chair you sit in and the body you live in is, out there in the dark, crushed into objects so extreme they sit at the very boundary of existence. It is a humbling and somehow intimate thought that the line between the ordinary and the impossible runs not through the substance itself, but only through its circumstances. The atoms in your coffee cup are not a different, gentler species of atom than the ones in a neutron star. They are the same kind of thing, capable of the same extremity, separated from that fate only by the mild conditions in which they happen to find themselves. Bury them in the collapsing core of a dying giant, and they would do exactly what the star's matter did: surrender their empty space, merge into neutrons, pack to nuclear density, join the crushed multitude. The potential for that extreme is latent in all matter, everywhere, including in you, waiting silently in every atom, expressed only when gravity gathers in sufficient quantity to call it forth. You carry, in the ordinary substance of your body, the same capacity that, elsewhere in the universe, becomes the most extreme objects that can exist. The everyday and the impossible are not different materials. They are the same material, living different lives. Matter is far stranger than it appears in our calm corner of the cosmos, and the neutron star is the proof, hanging in the sky, a monument to what your own substance can become. It would be easy to let all of this settle into pure dread, to dwell only on the annihilating gravity, the impossible density, the knife's edge before the abyss. And there is genuine awe-tinged fear in those things, a proper humility before objects so far beyond our scale. But there is another way to hold the neutron star, and it is closer to the truth and a great deal more wondrous. Because what a neutron star really represents is not menace but the staggering creativity of the universe. Its capacity to produce objects and conditions and states of matter so extreme, so beautiful in their strangeness, that they expand our entire sense of what is possible. The cosmos did not have to contain such things. It did not have to be the kind of universe where the death of a star leaves behind a city-sized sphere of nuclear matter, spinning hundreds of times a second, wrapped in the strongest material in existence, hiding an ocean of frictionless superfluid and a core of unknown exotic substance, balanced at the very edge of collapse. But it is such a universe, and that is a marvel. Think of everything that had to be true for a neutron star to exist. The laws of physics had to be just so. The quantum rules that let neutrons resist gravity, the strong force that binds nuclear matter, the precise balance of forces that allows matter to halt its collapse at exactly this extreme point rather than sailing past it or never reaching it. The universe had to be the kind of place where giant stars form, live, and die in collapse, where the conditions of that collapse forge neutron matter, where the resulting objects can persist for ages, spinning and pulsing in the dark. Every neutron star is a demonstration that we live in a cosmos rich enough and strange enough and finely tuned enough to produce wonders at the very limits of physical law, objects that test the boundaries of what matter can be. To find that frightening is natural, but to find it only frightening is to miss the larger truth, which is that we are fortunate to live in a universe capable of such extremity, such richness, such astonishing variety in the forms that matter can take. And there is a strange endurance to these objects that adds to their grandeur. A neutron star, once formed, does not quickly fade. It begins blisteringly hot, born in the fire of a supernova, and it cools only very slowly over enormous spans of time, persisting as a recognizable object for hundreds of millions or billions of years, gradually slowing its spin, gently dimming, but enduring far longer than the star that made it ever lived. The giant that collapsed to form it might have shone for only a few million years. The neutron star it left behind can persist for far longer than that. A long, slow afterlife of the star, spinning quietly in the dark, outlasting by a vast margin the brilliant but brief existence of the giant whose death created it. In this sense, the neutron star is one of the more permanent things the universe makes. A dense, durable remnant that can sit in a galaxy almost unchanged while generations of ordinary stars are born and die around it. A quiet, lasting monument to a single, ancient catastrophe, keeping its slow time long after everything that witnessed its birth has itself passed away. And there is something genuinely thrilling in the fact that we know about them at all. For nearly all of human history, no one had any inkling that such objects could exist. The idea of matter crushed to nuclear density, of a star compressed to a city, of a teaspoon weighing as much as a mountain, would have seemed like pure fantasy, beyond even the wildest imagination. And yet, through patient observation and brilliant theory, we figured it out. We predicted these objects before we ever saw one, deduced from the laws of physics that such things must be possible, and then we found them, detected their pulses, sweeping across the Earth, mapped them across our galaxy, even caught the ripples in space from their collisions. We, small and brief and made of that same fragile, empty matter, have come to understand objects so extreme that their interiors lie beyond any experiment we could ever perform. That is not a cause for fear. It is a cause for a deep and quiet pride. The pride of a curious species that has reached out with its mind and grasped the most extreme objects in the cosmos and understood them. Consider the strangeness of that achievement for a moment longer. We are small, soft creatures living on the surface of an ordinary planet made of the gentlest kind of matter, with lifespans of mere decades. We have never been anywhere near a neutron star, and we never will. Nothing we could build could survive within a vast distance of one. And yet, from our small and gentle world, using nothing but light gathered in telescopes, ripples felt in delicate instruments, and the reasoning power of the human mind, we have worked out the existence, the structure, the behavior, and the inner workings of these objects in extraordinary detail. We know their densities and their masses and their sizes, the speed of their spin, the strength of their fields, the layers of their interiors, the rules that hold them up, and the limit beyond which they collapse. We have, in a real sense, mapped the insides of objects we can never touch, on the far side of impossibility. And we did it from here, from this quiet planet, with curiosity and mathematics and patience. There is something genuinely moving in that, the spectacle of a small, brief, fragile creature comprehending the most extreme matter in the universe, the gentle understanding the violent, the soft grasping the crushed, the mind reaching out across the dark to hold a dead star in its understanding. So the dread that a neutron star naturally inspires can be held alongside something larger and steadier. Wonder at the reach of the universe and the reach of our own understanding. Gratitude for living in a cosmos strange enough to make such things, and clever enough in us to comprehend them. The neutron star is terrifying, yes, in its scale and its violence and its proximity to the abyss. But it is also magnificent, a triumph of cosmic creativity and human curiosity alike. One of the great wonders of a universe, far stranger and more extreme than our gentle corner of it would ever suggest. It is no accident that thoughts like these settle most deeply in the quiet of the night, when you might find yourself gazing up at the stars or simply lying in the dark, letting your mind drift out toward the vast and strange universe beyond. In the busyness of the day, a neutron star is an abstraction, a curiosity, easily set aside. But at night, in the stillness, the scale of it can be felt more fully. The genuine strangeness of knowing that out there, scattered across our galaxy, are thousands of these impossible objects, the crushed remnants of dead giants, spinning silently in the dark. Each one, a teaspoon, weighs a mountain monument to the extremes of physical law. And among the points of light you can see in the night sky, here and there, hidden among the ordinary stars, are these dead ones, these neutron stars, mostly too faint and small to see directly, but real, present, scattered through the same sky you have looked at all your life. It changes the character of the sky to know this. We tend to think of the night sky as a peaceful place, gentle and serene, a field of soft and steady lights. And from here, at our safe distance, it is peaceful, beautiful, calming. But it is also, in truth, a field of extremes, a place where some of the most violent objects in the universe hang quietly among the gentle stars. Scattered across that serene-looking sky are the spinning corpses of giants, objects of crushing density and annihilating gravity, sweeping their beams through the dark, occasionally cracking their crusts in starquakes, sometimes colliding in cataclysms that shake the fabric of space. The peacefulness of the night sky is, in part, an illusion of distance, the way a raging storm at sea can look serene from far enough away. The violence is real, and it is up there, woven through the same sky that has soothed and inspired human beings for all of history. And there is something awe-inspiring, rather than frightening, in holding both truths at once: the gentleness of the sky as we experience it, and the extremity of what actually fills it, the calm's surface and the violent depths, together in the single field of stars above you. When you look up now, you can carry that knowledge with you, and it deepens the sky rather than darkening it. Those points of light are not all living stars. Some are the corpses of giants, crushed to nuclear density, spinning hundreds of times a second, sweeping their lighthouse beams across the cosmos. The sky is not just a field of gentle lamps. It is a place of extremes, of objects so violent and so dense that they defy imagination, all of it hanging there above you, part of the same universe you inhabit. And yet there is a quiet beauty in knowing this as you look up, a sense that the familiar sky holds far more than meets the eye. The same stars your ancestors gazed at, the same constellations that have guided travelers and inspired poets for thousands of years, are accompanied, hidden among them, by these crushed and spinning remnants, these monuments to the deaths of giants. The sky has not changed. Your understanding of it has. The points of light are the same. But now you know that woven through them are some of the most extreme objects in all of existence, dead stars keeping their precise time in the dark. And that knowledge does not diminish the sky's beauty, but deepens it, adding layers of meaning to a view that might otherwise seem merely pretty. To look up and know what is truly out there, the living stars and the dead ones, the gentle lights and the crushed remnants, is to see the sky more fully and more truly than someone who sees only decorative points of light. The neutron stars you cannot see are part of the sky's grandeur, and knowing they are, there is a gift, a deepening of the oldest and most universal of human experiences, the simple act of looking up. And yet, knowing this need not frighten you, because of the one fact that wraps all of this strangeness in safety: distance. The nearest neutron star is hundreds of light years away, an almost incomprehensibly vast distance, far too remote to pose any threat to you or to the Earth. These objects, for all their violence, are spread across the enormous gulfs of the galaxy, isolated in the deep, dark, untouchable and untouching. Their extremity is real, but it is also remote, sealed away by distances so great that it can only reach you as knowledge, as wonder, as a faint pulse of radio detected by a telescope, never as any danger. This is worth holding on to whenever the cosmos starts to feel threatening, because it is true of nearly all the universe's violence. The most extreme and terrifying objects in existence, the neutron stars, the black holes, the exploding giants, are almost all unimaginably far away, separated from us by the vast, protective emptiness of space. That emptiness, which can seem lonely or daunting when you think about the size of the universe, is also a kind of shield, a buffer of distance so enormous that the violence of the cosmos is held at arm's length, reaching us only in gentled, attenuated forms, as faint light, as weak signals as the subtle ripples of distant catastrophes. We get to observe the most extreme objects in the universe from a position of near-perfect safety, studying their violence as something distant and abstract, a spectacle viewed from immeasurably far away. The same vastness that makes us feel small also keeps us safe, holding the crushing densities and annihilating gravities of the cosmos at distances so great they can never touch us. The neutron star is one of the most dangerous objects imaginable, and you are utterly safe from it. And both of those things are true at once because of the merciful enormity of space. And so bring it home now, down from the crushed stars and the impossible densities to the quiet, safe, ordinary place where you actually are. Because for all the violence of a neutron star, none of it touches the gentle reality of your own life. You are here in a calm corner of a calm world, made of comfortable, empty, everyday matter, in no danger from the extreme objects scattered across the distant dark, the crushing gravity, the annihilating density, the knife's edge before the abyss. All of it is out there, far away, doing what it has always done, while you rest here, held softly by the gentle gravity of the earth, your atoms full of their familiar empty space, your body whole and unhurried and safe. The neutron star asks nothing of you. It threatens nothing in your life. It is simply a wonder to contemplate from a safe and enormous distance, and then to set gently aside. There is a deep comfort available in that contrast. If you let yourself feel it, the comfort of the gentle against the extreme. The universe contains objects of unimaginable violence, and you are not among them, and neither is anything you love. You live in the mild middle of things, where matter rests in its comfortable, spacious, everyday forms, where gravity is gentle enough to walk in, where the worst extremes of the cosmos are distant rumors carried to us only as faint, light, and clever deduction. The neutron star is a glimpse of how strange and severe the universe can be, and that glimpse, rather than frightening you, can deepen your appreciation for the gentleness of your own small corner of it, the quiet miracle of a world where matter is soft and roomy and kind enough to build a life in. There is, in the end, a kind of tenderness available in this contrast, a way of looking back at your own ordinary world with fresh appreciation. We rarely notice how gentle the conditions of our lives are, how forgiving, how mild. We do not marvel that the ground holds us up without crushing us, that our atoms keep their comfortable empty space, that gravity is weak enough to walk in and strong enough to keep us from drifting away, that matter sits in its soft and stable, everyday forms all around us. We take all of it for granted. But the neutron star throws it into sharp relief. It shows us, by contrast, just how extraordinary and rare and precious the gentleness of our world really is. How unusual it is to live in a place where matter is calm and spacious and safe, where the violence the universe is capable of stays far away in the distant dark. To contemplate a neutron star is, in a strange way, to come home to your own world with new eyes, to feel, perhaps for the first time, how lucky it is that the matter you are made of and the world you live in rest in the gentle middle of things, far from the crushing extremes that the cosmos can produce. The dead star, terrifying and remote, becomes a kind of gift, a reminder to cherish the soft and ordinary miracle of an unremarkable, unhurried, uncrushed life. So let the strangeness soften now into wonder as the night deepens around you. Somewhere out there, hundreds of light years away or more, a neutron star is spinning in the dark. A city-sized sphere holding more than the mass of the sun, its surface flatter than glass, its crust harder than anything else in existence. Its interior, an ocean of frictionless superfluid, wrapped around a core of unknown and exotic matter. The whole impossible thing whirling hundreds of times a second and sweeping its beam across the galaxy. It has been doing this for ages, long before you were born, and it will go on doing it for ages more. Indifferent, silent, extreme, a frozen instant of catastrophe held forever at the edge of the abyss, and it cannot touch you. It is a marvel to know about, and nothing more. A piece of the universe's strangeness that you can hold in your mind for a while and then release. Let your breathing slow and let the impossible numbers fade. You do not have to hold the weight of a teaspoon that weighs a mountain. You do not have to stand in that crushing gravity or descend through those bizarre layers or peer into that unknown core. You can simply rest in the knowledge that such things exist, out in the deep, that the universe is far stranger and more extreme than your gentle surroundings would ever suggest, and that this strangeness, rather than threatening you, is a kind of gift, the gift of living in a cosmos vast and varied, and wonderful enough to crush stars into spinning spheres of nuclear matter and scatter them through the dark. Hold, for one last moment, the simple image that began all of this. Teaspoon that weighs as much as a mountain, because it contains the whole wonder in a single picture. An ordinary spoon, an everyday object, holding a substance so dense that it outweighs a peak of solid rock. A substance that exists only in the crushed hearts of dead stars and could never survive a moment in our gentle world. That single impossible image is a doorway into one of the most extreme realities the universe contains, the densest matter that can exist, the gravity that would flatten you to atoms, the spin that whirls hundreds of times a second, the strange interior of superfluid and unknown exotic stuff, the knife's edge before the abyss. All of it captured in the thought of a teaspoon you could never lift. And the fact that such things are real, that the universe truly makes them, and the fact that we, small and curious, have come to understand them, is among the most remarkable truths there is. A truth worth carrying gently into the dark, not as fear but as wonder. Picture it one last time, softly, without fear. A dead giant's heart, crushed to the density of an atomic nucleus. A sphere you could drive across in minutes, holding the mass of an entire sun, spinning silently against the backdrop of the stars. Its lighthouse beam sweeping the cosmos, tick, 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 with the precision of a perfect clock. A beat that has been keeping time in the dark for longer than there have been human beings to wonder at it. It is one of the strangest things the universe makes, and it is real, and it is out there right now. And you, here, safe and warm and made of gentle empty matter, have spent this night coming to understand it, which is its own small wonder. And now you can let it go and let the dead star spin on without your attention while you turn toward rest. There is nothing more you need to do tonight. The neutron stars will go on spinning, scattered across the galaxy, pulsing their steady beats into the dark, balanced forever at the edge of the abyss, whether anyone is watching or not. The universe will go on making them, in the deaths of distant giants, crushing matter to its limit again and again across the vast reaches of space and time. And none of it requires anything from you. You can let it all continue, out there in the extreme and beautiful dark, while you release the day and drift towards sleep, a small, warm creature of soft and spacious matter, resting safely beneath a sky that holds, among its gentle lights, these impossible spinning monuments to what matter can become. The teaspoon weighs a mountain, the star is crushed to a city, the dead giant spins in the dark, and you are here, safe and whole and held by the gentle earth, free to marvel at the strangeness of it all, and then to close your eyes and rest, while the neutron stars keep their ancient, precise, silent time across the deep, exactly as they have, all along and will, long after this quiet night has passed into morning.